Perfect. Hello, everybody. My name is Loren Shure, and I'm the first person hired at MathWorks. As such, it's in almost 35 years, I've contributed broadly to many of our products, including making some additions to the MATLAB language. I'm excited to be running masterclasses live on YouTube 2 this May and 2 coming in October. My goal is to help you learn tips, tricks, and best practices so you can get the most out of MATLAB. And to make sure you don't miss any of these sessions, please subscribe to the MATLAB YouTube channel to watch the next sessions live. Thank you. Okay, well, today I'm going to talk about one of the 2 techniques in advanced programming techniques. So this week, I'm going to talk about memory and what you, as a MATLAB user, MATLAB programmer, would benefit from knowing about how MATLAB uses memory. And to follow on that in 2 weeks, I'll be talking about the kinds of functions there are in MATLAB, and I'll also talk about them in relationship to what they have, what their implications are for memory. And then in the autumn, I'll be talking about some other programming things. So please put your questions in the chat and we will try to answer them. You will get access to the slides and code from there should be a link near the chat that you can use to download the materials. So advanced programming techniques. I'm going to just do the first one today. I'm going to talk about MATLAB and memory and what you as a programmer in MATLAB really should know. And I'm going to talk about passing arrays and things like how structures are structured from a memory point of view. And the functions we're going to ignore until 2 weeks from now. So my plan here is to have a slide for each topic within memory and then have a MATLAB example that I'm going to run in my MATLAB that you see sitting in the background here. So when MATLAB passes arrays to functions, what's going on? Does MATLAB make copies? Does it not make copies of the arrays? And the answer is not necessarily completely what you might expect. So here I have a typical function in MATLAB. You see it's function foo, well named, of course, 3 inputs and 1 output. And you see on the first executable line, I'm changing an element of the second input, and then I'm computing what looks to be like a straight line. And then when I go to call this, I call it, and these, in this case, I'm calling it with parameters that are temporary variables. But let me talk about what's going to happen in MATLAB. Well, when we pass arrays into functions, and by array, I mean any kind of MATLAB entity, because all MATLAB entities are arrays. They might be a scalar, they might be a vector, they could be an m by n by p by q matrix, it could be an array of structures. So anything in MATLAB getting passed into a function. And the mental model that you should have is that MATLAB will call any function as if it's making a copy of all of the inputs before it calls the function. So if the function messes around with the inputs in some way, it doesn't affect your original data values there. But that would be very memory unfriendly. It would use a lot of memory potentially if your X's and A's and B's were big. And so what we do instead is something called lazy copy or copy on write. So we send in basically the original data in its original location, and only if it's changed do we sever the relationship between the variable that you called with and the variable inside the function. So let me show you what this means here over in MATLAB. And I want to, I think I want to make my font a little bit bigger for you here. I should have thought of this before, sorry. Let me come to my preferences, my fonts, and let's make this go up to, let's see if 22 does well. 24 is a little bit more than I want. Apply, okay. That might be a little bit better. Okay, so I have a function foo. It's got 3 inputs and 1 output. Same exact thing that I had on the slide. So now I'm going to put some variables into my workspace. X is 1 to 3. AA equals 4. BB equals 2. And what you can see here is I've now created some arrays in MATLAB. And this is not a trick question, but I want you to think about this and count them with me. How many arrays did I just create? Never mind that some of them are scalar arrays. I made 3 things, 3 arrays in MATLAB, XX, AA, and BB. Now, I'm going to call foo on using these, XX, AA, BB. But before I do that, I'm going to actually come into the editor and put a breakpoint at the first executable line in my function. And so even though I've typed this line, yy equals foo, da, 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 it hasn't executed yet. So I still have only my 3 variables in MATLAB. Okay, and now I'm going to call foo because I'm going to press enter. And when I press enter, I come into foo, and you'll see it stopped on line 2, but it has not executed line 2 yet. Okay, so at this moment, from a conceptual point of view, MATLAB now has 6 variables. It's got the double letter variables in the main workspace, XXAABB. And then it's got their equivalent XAB in this function workspace. But from a physical point of view, at this very moment, X and XX are identical, and the same with the A's and the B's. So from a physical point of view, there's only 3 variables in MATLAB, even though I have 6 variables conceptually. And now I'm going to come to the editor part of the tab, and I'm going to say, let's run a step here. And now I'm sitting on line 3. I haven't executed line 3. And now from a conceptual point of view, I still have 6 variables because I didn't change. I didn't add any new variables here. I changed one of them. And that change triggers things so that now A and AA cannot share the same memory because one's different than the other. And so now from a physical point of view, instead of having 3, I now have 4. Okay, so let me step again. And now I've executed line 3, and I'm ready to head out of the function. And so at this moment, how many variables in all of MATLAB? From a conceptual point of view, I have 7. I've got 4 now in my workspace, X, A, B, and Y in my function workspace. And I have my original 3 double letter ones in the main workspace. So I have 7 from a conceptual point of view. From a physical point of view, I have 5. And now we're done with the function, so let's continue. I'm back at the MATLAB prompt here. And now how many in all of MATLAB? And the answer may surprise some of you, but maybe not. It's 4. I have my XX, AA, BB, and YY. In fact, if I type who, you can see what variables are in that workspace. And what happens in any function workspace once we leave it is anything that got created in there that's not being sent out is basically goes away. It gets cleaned up. So the copy that I had essentially of this scalar went away. Now for a brief moment, when I was leaving the function foo, y and yy shared the same memory, and then foo got rid of its connection to y because it was cleaning up, but yy retained it. So let me review that really quickly for you. We started off with 3 variables, and then we called foo. From a conceptual point of view, we went from 3 to 6 to 7 to 4. So 3 to 6 to 7 to 4. From a physical point of view, we went from 3 to 4 to 5 to 4. Why am I telling you this? Like, this seems sort of dumb in some ways. Well, think about it. X was maybe my data here, where I'm trying to locations where my data are, where I'm trying to produce some calculation, in this case, a straight line. I never changed X. I used it, but I never changed it. So if X was, I don't know, a terabyte, it wouldn't make an extra terabyte copy here. Of course, once I calculate Y, that's going to take a terabyte and use more memory. But A being a scalar, yes, it's going to take more memory, but not very much. So we're not so worried about that. So hopefully that makes some sense to you. And while I'm in here, I'm just going to show you a little bit about the way I use MATLAB. So I use MATLAB where I have the quick access toolbar here, and I can click in it. It's normally up here, and you can see all the tabs from the desktop because I have a whole bunch of shortcuts I like using, favorites. So I move it below the tool strip, and then if I want to minimize the tool strip, I still have what I put over here, anything I want. And you'll notice that I have some things from, let me just bring this down again. Here. You'll notice that I use Run in Advance so often that I already added it to my quick access tool strip here. So that's really a nice handy thing. And I have another one, this is really helpful, which clears my workspace, makes my cursor from my command window go to the upper left-hand corner for me, and it closes all my open figure windows. So if I go like this, now I have nothing in my workspace and nothing in my command window. So I'm sort of free to move forward. Okay, next problem we want to talk about in MATLAB from a memory point of view is, when does MATLAB do calculations in place? So by that I mean, I have an input variable and then I'm going to use that same name as an output variable maybe. And if I do that, well, let's suppose X is a terabyte again, and I have a clean workspace. I started with a terabyte, and then when I'm done, I end up with a terabyte because this isn't changing the size of the array we're working on. So I have a terabyte in, terabyte out. If I say Y equals same thing, but the new expression, same expression, I have X in and Y out. So I have 1 terabyte in and then 2 terabytes for X and Y on the way out. So the interesting question is, okay, but what happens in the middle here? And that is an answer that is not straightforward, but it's not difficult either. So, oops, let me come and show you some code here. So in order to answer this, I'm going to show you a function I have that is going to create a large array. And then you'll see I'm going to call 2 different functions. Excuse me 1 second. Okay, 2 different functions, myfunc and myfunc in place. And you'll notice in both those cases, I'm using XX as an input and XX as an output instead of putting the output in a new variable. And here are my 2 functions. They're actually the same as each other, except for A, the name, and B, the output variable. In myfunc in place, I'm reusing the input variable name as an output variable name, and I'm using a new variable name in myfunc. So I want to show you how this works. So let me come over here, get rid of foo. And now this is myfunc in place. And let's talk about this function. It's the same one I had on the slide. You probably know that dot up arrow does an element-wise square. So if I have the elements 1, 2, 3, 4, I'm going to get 1 squared, 2 squared, 3 squared, 4 squared. Okay. Okay. So I'm going to basically take XX and square each element and multiply times 2, and then add to that 3 times each XX element, and then add the scalar 4. So if you think about it, suppose this could be true in n dimensions, but I can only draw with my hands in 2. So think about the ij element on the input. What does it influence for the output? What it influences is the ij element and nothing else. So I tend to call these things element-wise functions because one element only affects the equivalent element in the output. Okay, so that's myfunc in place, and here's myfunc. Same exact thing, but I'm putting the output into a new variable name. And so I'll get rid of both of those. And now here's my show in place, and ignore the debugger stuff right now. I'm going to in fact, I'm going to make this bigger so you can see the whole thing right now. I'm going to set up an array, just make up some random numbers here. I'm going to first call myfunc with X as the input and X as the output. And then I'll do the same with myfunc in place. And then I'm going to call them each with separate names for the left-hand side. So I'm going to call myfunc with a Y and then with a YY. And I think... Oh, interesting question. So someone just asked if you have to close a function, terminate a function with an end statement. You do not have to, but in this case, it's a great question, by the way, and it's something I will cover in 2 weeks, but I'm happy to talk about it here momentarily. I can put it there, and it doesn't change the meaning of this program, but there are times when you have to use end statements, and that won't be today. It'll be in 2 weeks. But if you have some code that is old MATLAB code that doesn't use end statements and you want to change them to use end statements, you can. If you're using, there's only one rule in, and this is, well, there's 2 rules. And I'll get into this more again in 2 weeks. But if you have more than one function in a file, if you terminate one function with an end statement, you have to terminate all the functions in that file with an end statement. And if you happen to be using nested functions, you must terminate them with an end statement, which means everything in that file that is a function needs to be terminated with an end. And if you don't know what function or nested functions are, come join me in 2 weeks. I'll be talking about them. But in the meantime, this end is completely up to you. It really doesn't matter. MATLAB won't be more or less efficient because of it. Either way. Okay, so I'm going to just run this code. And oh, and then I said I was going to call the regular one with y and yy as output, and then I'm done. So let me run this. And what I want to do now is I'm going to bring up the Windows Task Manager. Okay, and I want to see what's happening with memory. So when I created this array here, I had a bump up in memory, and obviously because I'm online, other stuff is going on my machine. So you may see the memory jitter a little bit, but that's just from my first one. Now what I want to do is I want to move from here, and I want to call my func with the same left-hand side as right-hand side. Whoops, I moved that and I didn't mean to. Let me go like this so that you can see what's going on. And let me continue here. And so we had one bump up because we made the array X. And now when I call my func, notice that it goes up again by about that same amount, but then it comes down because we're replacing the old X with a new X. And now we're going to go do the in place version. And when we do, if you look here, it now did it in place, and there wasn't a big bump in memory. And now let me do the last one where I'm going to call the in place version, but with I'm going to call the regular one with a new left-hand side. Let's do that. And when I do, we see the memory go up again because it needs a chunk of memory the size of X. Okay, so it went up as far as this one did, but it's staying up. And now I'm going to call my func in place with a new left-hand side. And because it's a new left-hand side, we bump up again. And now I'm near the end of the function. And so I'm going to hit continue. And that's going to say finished. And we're done. And you see when we finish, MATLAB gives all that memory that we were using inside this function for XX and for Y and YY. And it comes back to me because the function is done. So here's the rule of thumb. If I have a function here that's calling another function here, and the input name is the same as the output name, both when I call the function and in the function I call, in this case it's not, then MATLAB will try to do the calculation in place. And it's like, oh man, Loren, why are you saying try? Don't you just do it? Well, we can't just do it because there's a relationship that has to be true between X the input and X the output for this to work. And if I were in a live audience with you, I would make you try to tell me what that is. But in the interest of not making it complicated through YouTube and all that, I'm going to tell you. And that is that X the input and the X the output have to be the same size and data type. Okay, so if X is a 1/3 double, the output X also has to be a 1/3 double. Imagine my input was an unsigned int, so 1 byte, and my output was a double, 8 bytes. Well, 8 bytes don't fit into 1 byte. Okay, and so that's why we need the data type, and we need it to be the same size. And if you're thinking in MATLAB, it even needs to be the same thing. Like if the input is full and not sparse, the output needs to be full and not sparse. So things like that. So that's one thing that needs to be true. And the other thing that needs to be true is we have to know an algorithm that will work. Okay, so it turns out for matrix multiplication, even if I'm talking about a square matrix and I say A equals A times A, there is no in-place algorithm that lets me do that. I actually have to make a new output to hold the new A, because if I start overwriting elements in my A while I'm doing the calculation, I will get the wrong answer. Okay, so we have to have a good combination of the right input and output relationship and an algorithm. Now, element-wise ones always work, so things like trigonometric functions and so on, and plus and minus and things of that sort. There's another class of functions that also works, and I'm going to attempt to show you by modeling it here on the video. So hopefully you can see me. And suppose we're using one of the cumulative functions in MATLAB. So that would be cum sum, cumulative sum, cum prod, cum trap z, cum min, cum max. Okay, let's suppose we're doing the cum sum. Now pretend I'm the array here, or I'm representing an element of the array, and I'm right now the 1, 1 element. Well, when I do a cumulative sum, the 1, 1 element is just the 1, 1 element. So I come over to number 2. The 1, 1 element is 1 plus 2. So I have 1 right next door, so I can take 1 plus 2, 1 plus 2, and replace myself with 1 plus 2. Let's see if that's going to work. Let me go to 3. 3 is 1 plus 2 plus 3. I'm 3. 1 plus 2 is right there. So I can take it, add it to myself, and replace myself. And so all the cumulative functions work, whether you're working them forwards or backwards, can take advantage of that. And so this is still pretty esoteric, because if I can do some of these things in place, that might not cover the whole calculation I'm doing. And so what we have found is that sometimes if you refactor your code and you say, oh, I've got some element-wise stuff, or I've got some stuff that could go in place and I have a really large array to work on, but that's in the middle of my calculation. So what you do is you can refactor your code into pre-processing function, and then the element-wise or whatever, the in-place stuff, and then a post-processing piece. Because often the pre-processing piece and the post-processing piece are not using every array to do everything. It might be padding one array with a few extra elements. And so I don't need copies of everything while that's going on. I might just need to make that one array grow. And so we found people who, if they were near the edge of something working or else going into virtual memory, which would slow things down, they were able, by refactoring, to make this work better for them without having to think about, let's go to a much bigger machine, or I have to buy more memory, or I have to use a parallel system. This is just within the confines of MATLAB. And so that's something that may help you once in a while, but it's a little strange. Okay. Now I want to talk about for loops and their performance and memory, because there's a link between performance and memory here. And suppose I want to try to calculate this matrix. The rows and columns are going to be the column, the row number times row number plus column number cubed plus 17. And I'm going to show it to you 3 different ways. I'm going to show how to create this array looping across the rows, looping down the columns, and vectorized, because there's different implications for which way you address the memory with MATLAB. And that's because we have to store the MATLAB array somehow. And the way we store the MATLAB array, I'm going to show you here. Okay, so let me do my little thing of clearing and closing things. And now you will see that instead of using a regular MATLAB code file that ended in .m, I now am, whoops, wrong way. I am now using something that ends in .mlx. And so I'm using it's It's not even a new feature anymore. It came out in 2016B. It's called the Live Editor, and it lets me create these beautiful documents here that have actual code in them too, but I get to tell a whole story here. So I said this on the slide. Let me show you how the MATLAB memory is laid out. And I see I have an extra space here. Okay, so I was telling the story in this. I used to be a Fortran programmer. I am reformed, but I was, and it was the way to. Okay, what is the case if output of the function has lesser bytes than the input? Say, so that's a good question too. If it's a different type, we just make a new memory. We don't overwrite it at all. Because we don't know at that point if it's going to work. So if you're going from a double to an int, there's no sense of in place because we don't want to use the whole array and just the first byte of each one. We want to actually compact it even more. So it won't do that in place memory thing. Another great question. Thank you for answering or asking, not answering, asking. Okay, so in the old Fortran days, I used to program in Fortran all the time. And so you really had to be careful in Fortran to arrange the code you wanted to run through your loops in the best way so that it used the memory as sequentially as possible. And that meant that you needed to know how Fortran stored arrays. And as it turned out, it stored it, if this is your array, column 1, column 2, column 3, it stored column 1, and then followed by column 2, and then underneath column 3, and so on, like a long string, column by column by column. And that's the way Fortran works. That's actually the way MATLAB works. It's not the way C works. C works row-wise. We could have made any choice at the time. Fortran was at that point a very popular mathematical and scientific computing language, and so we did what they did. Okay, so let's just see if I try to run the loops in different orders, is there some implication for that? So I'm going to make my array have. I'm going to time it here. So that's just making the time thing because I'm going to time 3 things. Remember, I'm going to time the loop, the inner loop going over rows, the inner loop going over columns, and then a vectorized solution. Okay, so I'm going to say I'm going to work on a 5,000 by 500 array, and then I'm going to time this. So my output array going by rows on the outside. So I'm doing a column at a time. I'm going over the columns each time. So I'm going across the rows each time, basically here, because I'm going across row 1 and then across row 2 and so on. So if I come here, one way I can run this, there's a lot of ways. You'll notice in the live editor, I can do that same run in advance and it's up here. But I can also just put my code, my cursor on this chunk of code, this section, and I can just run and you can see that it had an indicator that it was running. Now I'm going to do the same straightforward loop. You'll see this is rows plus times rows plus columns cubed to 17. And now I'm going to get the column version and we're going to time that. That's what the tick-tock is doing. And now I'm going to do the vectorized version, which is creating my number of this is my number of rows. This is my number of columns. And so I'm going to I have to do transposes and things to get things right. And I'm going to time that. Now, before we even worry about the times, we better make sure we computed the same things. So that's what I'm doing here with is equal. I am making sure that everything got computed correctly. And here are the execution times. So the first one took about 4 seconds. It took a little bit longer going across the rows than down the columns. And the vectorized one was even faster. So the order that you do loops is important. Now, you might say, depending on how often I run this, if I run it again, I'm going to get a different answer because MATLAB begins to learn things as it runs the code. So it might go, if I come here and we do this again, let's do this and this and this and this. And now you see that, so there's some difference there. And now you can see there's really a bigger difference here between the columns versus row version. And I can try it one more time. I don't know that it's going to make a big difference, but let's try it one more time. N. So it makes difference. It depends what jitter is going on my computer at the time too. So I don't want you to learn from this that you should never use for loops. Sometimes it's the best way to express something. Sometimes it's the only way to express something. Not everything can be vectorized like I did here. But what I do want you to be aware of is that making sure you go down the rows so that you're addressing the elements in order is faster. And that will always be faster if you go down the rows than across the columns because of the way the memory is stored for MATLAB. So hopefully that is helpful to you. While I'm here, I'm just going to take advantage of the fact that this is a live script and show you one more thing about it. I can actually export this when I'm done, and I can export it. I'm going to zoom up. Let me zoom out. Let me hit export and zoom in again. And you'll see I can now take my document and export to PDF, Word, HTML, or LaTeX. And I also have a whole bunch of other things that I can do in there that I'm not going to talk about. But it's a really nice way to get your thinking straight. So I encourage you to look at it if you have stuff that you need to document, whether it's for your professor, or a paper, the outline of a paper you're trying to write, or for your boss or whatever. Okay, let me move on. So right now up until now I've talked about numeric arrays, which is what was the only thing that existed in the first versions of MATLAB when I used it. But the real world doesn't really work like that. There's other information that's pertinent to what we're doing. So suppose I'm doing an experiment. I want to collect the data, but there's often metadata that I also want to have associated with it. For example, I might want to know what the ambient temperature and barometric pressure are, or something like that. I might want to know the name of the person who's taking the measurements, whatever. And those things are different than the data themselves. And so I might like to somehow take all of my data, which might be maybe some time sequences. Maybe I'm getting a data point every second for 100 seconds, and I'm getting some other thing, a voltage. And then I also want to put, like I said, the experiment person's name and the temperature and pressure there. And so I want to kind of have that all get collected together. And we have at least two ways, actually three ways, to collect things together very nicely. One is with a cell array, and one is with a struct. And I'll talk about tables in just a few minutes. So let me just start with only one piece of data that we're going to worry about, my numeric data here. And I have really tiny amount of data here, obviously. It's a double array, even though it looks like integers. MATLAB, when you input numbers, they are doubles. And I have a double array. And then I'm going to take that same array and I'm going to put it into a cell of a cell array. And then I'm also going to take that same array and put it into the D field of a structure. Now, for those of you who don't know what cell arrays and structs are, let me give you my analogy that I think will help you. So everything in MATLAB is an array, which means it's regular. It's M by N, or M by N by P, or M by N by P by Q by da 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 da, so on. Okay. Well, cell arrays and structs are too. Okay. So this cell array actually happens to be a 1-by-1 cell. It's a scalar array. But I could, like when I was a kid, I would steal an egg carton when it was empty sometimes before it went into the trash. And I would put my pennies in one of the sections, and I would put feathers in one, and I would put white stones that I found in another one, and some of them would be empty. And what unified these things, kind of like the experiment, is that was my stuff, okay? And I didn't want anyone touching my stuff. And if you think about it as a cell array, well, my egg crate was, in my case, it was 2x6, and I could, if I told you to get the feathers and you couldn't look inside to see, you would want to know, oh, it's in row 1, column 3, or something like that. So I could do that. But if instead of one of the dimensions I have names, I could think about the very last dimension, instead of being the final column, let's say, if I give it a name, I could instead store something in this box, and each of the little areas would have names in them. And those names might be pennies, dimes, feathers, stones, and so on. And then I could say, get the stones out of the stone section, and you would know what to do. So that's the idea between cell arrays and structs. And because they're a container holding my other stuff, they're going to take up a little bit more space than just the original stuff. Okay, but the question is how much? And I want to talk about that now. So for everything that I'm going to talk about, I might refer just to a cell array, or I might refer to a struct, but they're basically very similar. And if I say something for one, it's true for both of them. So let me come over here and let's clear everything out. And let me clear all the output. Okay, so here we have my array that I'm going to make, and the cell array and the struct, and you can see them there. And the question is, I just told you which one's going to be biggest. Well, I don't know, but I'm pretty sure, I hope I've convinced you without thinking at all about it hard, that D is the smallest of these. And the question is, okay, between a cell array or a struct, which one's bigger and which one's smaller? And usually I make people vote. So think in your head, which one you think might be bigger and why, or smaller and why. And then I will come over here and run this for you and explain what's going on. So let me make that a little bit bigger so you can see it. So you can see my cell array takes up 16 bytes. It's my double array, sorry, takes up 16 bytes to 8 bytes for each double. And then on top of that, my cell array, which is only a 1 by 1, has 104 more bytes. Well, what is being taken up in those 104 more bytes? Well, it has to know information about what it's holding. So what's in there is something that's a 1 by 2 array. It's double, it's real, it's full and not sparse, real, not complex, and so on. So we need some information about that. And that's the minimum amount we need as 104 bytes of overhead. If you have something that's highly dimensional, like 1 by 3 by 7 by 20 by a really long set of dimensions, it might take even more space. And then you'll notice the struct, which really only holds the same stuff, is another 64 bytes more than the cell array. So I'm going to come here, I'm going to put a section break, and I'm going to start typing something because I want to explain what's going on. Name length max. Okay, this is a function whose name you probably have not heard of. And there's good reason. There's no reason you need to know it normally. It has an answer of 63. Okay, let me come here and let's get help on name length max. And here you see it's the maximum identifier length in MATLAB. Well, what's an identifier? An identifier is the name of anything in MATLAB that you need to know about so that you can refer to it, so that you can tell MATLAB what you want it to do. So that means it needs to be variable names, the field names of MATLAB structures, scripts, functions, class names, Simulink model names. It's not the name of data files. That's different stuff. But this is basically the names that you need in MATLAB here. And you'll notice that it's 63. We tried to make it big enough so that you could make names that were expressive, but not so big that we're wasting a lot of memory because most people only use 3 or 4 characters. Okay, now it turns out that this is 64 bigger and not 63 bigger. And that's because now I'm letting you in on an implementation detail you kind of don't need to know, but why not tell you? It's not hurting anything. We saved the final byte here, the last byte, the 64th byte, for what's called the null terminator, because it's written in C, and in C, the convention, that's the convention you use so you know when a string is ended. So we make sure there's always room for a null terminator, so we can never get over 64 that way, or over 63 that way. Okay. So now we know that a double array takes less memory than a cell array with the equivalent data, and the struct takes a little bit more space on top of that. Okay, but I've only had scalar arrays here so far. This is a 1-by-1 cell. This is a 1-by-1 struct. But MATLAB, which you probably know stands for Matrix Laboratory, is actually an array-based language. And so I can make arrays of these things too. And so I want to talk about how we store things in structures that are not, that first of all have more than one field. And second of all, we'll get to what happens when we have arrays of them. So I'm going to make a scalar struct again this time, but I'm going to have two fields, not just one, an A field and a B field, and it'll be big. And then I'm going to say S new equals S, and we'll see what happens with memory in MATLAB when I make that copy. And then I'm going to change one element of one field of S and see what's going on. And so I'm going to come over here. I'm going to shorten this. I'm going to bring back our task manager there so that we can see the memory here. Okay, so I'm going to, now you'll notice that instead of running things in place, I'm running things side by side now. That's another way you can run here. Okay, and I'm going to create a structure here. And you'll see that on the memory gauge that the memory goes up a bit, one little step. And now when I create B, it should go up by that same amount because it's the same size array that I'm putting in there. And now I'm going to make a copy. I'm going to say S new equals X, S. And to me, if you think about it from a logical point of view, it should go up by those same two steps because I'm making copies. But we also talked about copies not always needing to be made, right? So what's happening here is we actually don't do anything here. I've got S new. It tells me that it exists now, but nothing happened in memory because at this very moment, S new and S are identical completely. And now I'm going to modify one element of one field of S. And the question is, do I go up by 2 bumps or 1? And let me do it while they're still on the screen. I think I ran it. Maybe I didn't. We go up by 1 bump. So let me clear this out again. And let me, now that I've talked through it, let's run through this faster. So I want to clear everything out. We get our memory back. Let's come up here. And I'm going to run the section in advance. So we're going to get 1 bump up. Oops, sorry. Now you know what happens. You get errors. Life happens. It's okay. Now I'm going to create my first field. There's first bump. You should see the second bump here. For B, here's S new, and nothing happens. And here's me changing S dot A and just even one element. And it's a little hard to tell here, but it's actually going only up by another one of these little steps. The granularity is not very easy to see here. And because if I did this, so I'll show you because I'll do this now, and let's run this as well. And when I do, it goes up again. So B had kept its connection. S dot B and S new dot B were connected until I made that change just now. Now, so what I want you to know is for every field in a structure, it contains its own MATLAB array. And that's why when I changed S dot A, it had to separate itself from S new dot A, but S dot B and S new dot B could be the same thing. And only when I modified the B form did we see that piece disconnect as well. And now I'm going to clear the memory out again. Okay, so I just said something kind of interesting. I hope that every field of a structure, and this means every cell in a cell array, are each their own MATLAB arrays. Why do you care? Well, the reason you should care is if you're passing one of these entities into another function, and that function's going to operate on some of it, it's only going to potentially change the fields or the elements of the cells that it touched. And all the other ones don't need to have extra copies made. So if you're trying to do something small in one little piece and you have really large amount of data that's part of this whole big entity, all that big stuff is not going to need to have a copy, just the fields, the small fields. Maybe you're fixing a date on the day of an experiment because it got entered incorrectly or something like that. It's not going to make a copy of all of the data because you're not changing that. It's only going to deal with the field or the cell that's changing right there. Okay. Another thing you will notice is that I went and changed my code here. I'm going to just show you briefly. I'm actually working with stuff in Git behind the scenes. And so if I wanted to, I could come back here and I could say, whoops, what was my original code? I could come, I will try one more time and then I won't. Current folder. Okay, it won't let me do it. I'm not going to worry about it. I can revert at any rate for those of you who are Git users if I want to. Let me go to the next topic here, which is, okay, those were scalar structures. It was S.A and S.B, but there was really only an S of 1, 1. I want to think about what happens when we have an array of structures. And to do that, I want to motivate it. So we all these days have cell phones with cameras, and we take pictures on them. And they basically get stored effectively as an M by N by 3 array, because we're doing things in color usually. And I'm not worried about compression right now. So it's not how many bytes it takes, but it's representing the size M by N. And if it's low res, it's going to be, you know, whatever you set it to be, 200 by 100. And if it's high res, it might be 3000 by 2000. So different M's and N's depending on the resolution, and then three planes afterwards, one for red, one for green, and one for blue. Okay, so I may be in a lab and I'm trying to collect some sort of information of the same kind, and I could take a picture and collect the M by N by 3 array. But there's devices that are put out by various manufacturers that may be more helpful, maybe more suitable than what I have available. And so if we use sensor number 1, they say, oh, well, we collect things because we have a really good red filter. We're going to and a really good green filter, we're going to make sure they're separated for you. So we're going to give you red, green, and blue, but instead of giving them in separate arrays, we're going to put them into one structure for you. And if you think about it, this array, this red plane is M by N, the green plane should be M by N, the blue plane is M by N. So I have 3 M by Ns, which is the same as M by N by 3. So same number of numbers right now. And then we have another equipment manufacturer who says they may have a great red filter, but we can collect more data more quickly because we use an array of sensors. And so we have an array of sensors that's M by N, whether it's, you know, again, 3000 by 2000 or whatever. And in each one of these, we store 1 red, 1 green, and 1 blue. So 3 numbers for each of these. So we have M by N of these and times 3. So it's the same number of numbers each way. So let me come over here in MATLAB. Let me do the usual, let's clear things out. We'll get rid of that right now. And I want to get rid of the output. Okay, so I'm going to come over here and I'm going to load an image. You just saw it, but you'll see it load in now. And we're going to use this pretty colorful image. And you can see it's 135 by 198 by 3. And it's only 80,000 bytes because it's not doubles, it's unsigned 8-bit. And in fact, if we come over here, I think it might say that. Its class is unsigned 8-bit. Okay, so now what I'm going to do, and I love this MATLAB code. This is one of the things that's so expressive about it. This says, take my array X, my image, and give me all the rows and all the columns in the first plane, second plane, and third plane. So I can come here and I can get the IM1 here. And now there isn't a really nice way for me to do the same thing for the IM2 version. So I'm going to use a for loop and I'm going over things in the right order here. So we're going down each row. I'm going the rows, you know, row 1, row 2, row 3, and then looping over the columns as we do that. And I'm putting the data in as we go. So the question is, I have X now. If we do a who, we have X, IM1, and IM2. I hope you'll grant me that X is going to be smaller than IM1 or IM2 because it's just M by N by 3, as we saw up here. Let's see what happens. So if you think about it, the way to think about this in my mind is to think about how many arrays are being stored. And if we think about IM1, there's an array for each field, right? So a red, a green, and a blue. So there's 3 fields. That's not that many. So if I come here, that's going to be a little bit of overhead. The overhead, remember, was 104. And then we also have to deal with the fact that there's a name there. There's 3 names there, in fact. And you can see that in my calculation for the overhead. IM2 actually has only 1 field, so it's going to be name length max plus 1. But instead of the number of arrays being 3, it's got m by n arrays, each of which contain a pixel. And so I've got m by n arrays here. So when we come and look at this, oh my goodness, look at this now. My IM2 is in the first 2 dimensions the same as my X. My IM1 is only a 1 by 1 array because it's a scalar struct, but it takes almost no more space than the original X, 500 bytes or so. IM2 takes a lot more. This is almost 3 megabytes, everyone. 3 megabytes for the exact same data that I can store in 80,000 bytes. And this is the calculation for the overhead here. So the first one, the IM1, has the overhead of 504, and the second one is almost 300 megabytes. Now, I don't want you to think that you should never, ever use arrays of structs. There are times when you should and can, and it makes sense. But I want you to know about them so that you don't mistakenly do it in the case where you don't need it, and therefore get a lot of extra memory bloat over that. Okay, so what do we do in this case with the IM2? Is there a way we could fix it? Well, I don't know if what I'm going to do next makes sense for images, but I'm going to talk about tables. And it says new there, but in fact, tables have been around since 2013. So it's not so new anymore. So hopefully you know about them, but my experience is that not everyone knows about them. So I'm going to show them to you. And I'm going to clear my workspace here, and I'm going to clear all the output here. Okay. And this data type is basically, think about spreadsheet. And as long as each column is homogeneous in terms of what it holds, MATLAB can put that into a table. And it supports very flexible indexing. When we introduced tables, we also introduced categorical arrays. These are for data that are essentially non-numeric. Think about something like colors like, our favorite colors. Mine might be purple, yours might be green. On the spectrum, there's different things where we could talk about the length of them or wavelength or something. But in terms of purely thinking about colors we like, there isn't one ordering that makes sense. It's really an unordered list. But there are things where it would make sense. If you're going to the store and trying to buy a coffee, you might buy a small, a medium, or large, with the expectation that a small holds less and costs less than a medium, which holds less and costs less than a large. Okay, so that would be an example of an ordered list, even though you don't have exact numbers for it, maybe. And so they can be very helpful when you're doing some of the work, too. And then I'm going to just mention briefly strings. They're a better way to work with text. They're relatively new. I think they came out in 2016, and I'll talk about them in just a minute. But I want to come over here and talk about the tables first. So I'm going to run some code here. You'll see I'm just putting in MATLAB arrays. These are each length 5 here. But my table is going to come out, and it's a 5 by 5 table. I didn't have to have the same number of rows as columns here, obviously. And you'll see the last name, they're all cells of a cell array containing a string. And then we have age, height, weight, and blood pressure. And notice blood pressure is 2 numbers in each row. As long as each row is a 1 by 2 double, then I can stack them up and get the output to be what I want. And the table is 5 by 5, and it's just pretty convenient to see what's going on there. Okay, well, if you have maybe saved some data that would be similar to this, and you'd want to maybe try them in a table, and you save them in a mat file, what I can do is I can load in my mat file here into a structure, if I give it a left-hand side. And you'll see when I hover here, everything is length 100, but there are different types. There's cell arrays, there's doubles, there's logicals. Okay, and so I can find out how many fields there are, or I could have come here and I could have counted them. And now I would like to say, well, what if I put that into a table instead? Well, I can use the struct to table function to get me there, which is very nice. And now you see I have a 100 by 10 table, and it doesn't, even though I left the semicolon off, it doesn't print it out. It lets us scroll through there, and we can see all the different column names and so on. Okay, and so now if we look in the workspace, we see that I have my structure, which is 1 by 1, and it takes a little bit less memory, but not much less than my table, which is 100 by 10. The table, just by telling me there's 100 rows and 10 columns, is helpful from that point of view. And the extra overhead is not huge. It was about 1,000 bytes. Okay, but if I add more rows, I'm not adding more overhead because each one of these columns has some overhead. So I've added a new column. That would be like adding a whole other variable to my structure. So of course it would take up another name in the namespace there and another one here. So if I add a column in either one of them, it's going to add some overhead as well as the data. If I just add rows, it's only adding data and no overhead. And so I showed you this, which is what the overhead was. Okay, now look what I can do. I can say, if we look in this table here, just looking at the top, we can see the ages are kind of bouncing all over the place, and even the last names aren't in order, and nothing's necessarily in order here. In fact, it probably is ordered by something that we didn't even leave in this table, like data visit or something. I don't know. But I can come here and I can sort my rows in the patient table by age. And when I do, we can find the oldest patient by just saying, give me the end one and all the rows, and we can find out about that person. But suppose, notice here, I have a bunch of 25-year-olds. Maybe I want to sort them in another way. Maybe what I want to do is, let me come here. Let me do it. Oops. Let me come here. And I'm not going to worry what I call it right now, but let me sort it by two things. Let me sort it first by age, and then by height. And let me run this again. And now you'll notice that I've got the 25-year-olds at the top still, but now they are increasing weight, and maybe not too shockingly, because women tend to be smaller than men more often, not all on average. The women here happen to be first. Okay, so, and I could add as many more variables as I want to sort if I want to do tertiary sorting on another thing, whether they're smokers or not. As long as the first two things are a tie, that's what would happen, is it would sort on the next thing. Okay, and then let me show you categorical. So what I'm going to do is, there's one field in the patient table that was self-assessed health status. And this is when you go in and there's those smiley and frowny faces, and you basically have to pick where you are on a spectrum. And I know, being scientists, we tend to think, or engineers, we tend to think, well, they said 1 to 5. I'm feeling 4.3. I'm not really a 4, but I'm definitely not a 5. They don't care. They just want to know, do you feel lousy or do you feel okay? Okay. So for their point of view, that's all they need. Excuse me. Now for my cell array of strings here, which is what they're stored in, it takes about 12,000 bytes. All right. And now I'm going to turn this into a categorical array, because I have 4 categories there, if you think about it. And I'm going to show you the categories that it thinks are held in that array: excellent, fair, good, and poor. And I didn't make it a structured array, a ordered list. You can do that. Just go to the help for categorical and you can find out how. And then when we look to see the difference in the sizes, you'll see my categorical array is also 100 long, but instead of 12,000 bytes, it's about 600 bytes. So if you're importing a spreadsheet, for example, and you have several columns that could be categorical, it may be to your advantage to make sure that they get imported as categorical rather than as carrying around the strings. And the nice thing is, I can do things like, I can say, sum up all the people who said they felt good, and there it is, and we can have an answer. So I can do logical, and if it's ordered list, relational operations on it. Excuse me. All right. Now, I talked about strings, and I want to come over back here to the strings. We introduced a new data type called a string in 2016. And what you'll notice here is we're using double quotes instead of single quotes. That's observation number one. Observation number two is I have an array of these things, and they're not inside a cell array. This is a string array, and it's a 1x3 because this is a 1x1 string and a 1x1 string and a 1x1 string. And the way it got created, they got created from a 1x1 string and another 1x1 string. And in the middle, we use implicit expansion to expand out the 1 through 3. So we make image 1, image 2, and image 3, for example. Okay. And we did this because we wanted to have better text processing capabilities that enabled us to release the text analytics toolbox, for example, and do some machine and deep learning with data of that sort, as well as numeric data or images or whatever. So it also is simplified text manipulations. So this is what I used to write. And believe you me, I've written this many times, this sort of thing. I want to see if the string dog is in my data set, my text data. And so I do a stir find, which will find me the location, the beginning location of where dog is. And it may be empty, or it maybe give me number 2 if it starts in the second index, or it might give me an array of indices 2, 3, 44, 99. And if it's not empty, then I found one. So it's in there. Really hard to read that code afterwards and remember what it does. So here's what you can do now. You can say, does text data contain my string dog? It's so much easier. I don't know about you, but I can kind of feel feel my blood pressure go down. I feel myself relax because I can read the code and I don't have to stress about what it's doing. So not only is the code about 50 times faster this way than this way, this one with a string and that one with a cell array of strings instead, but this is also strings tend to save about half the memory over cell arrays of strings. So let's come and see this. So now I'm going to turn my healthcare cell array of strings into a string array here. And now you'll see we have 100 by 1 string array, and we get about a factor of 2 savings in the string. And I still get the properties so that I can do the logical operations that I expect to be able to do. How many people said they felt good? And that's however many. All right, just about done here. I just want to tell you that today we talked about MATLAB and memory and how MATLAB passes arrays to functions. And I told you it was by value. We call the function as if we made copies, but we do it with a lazy copy or copy on write paradigm. So we only make the copy when we actually need to. And I showed you that sort of wacky in-place optimization code pattern where the input name and the output name have to match in 2 different locations when you call it and where it's being called. And then we try to do it in place because not everything can be done in place. So we will if we can. And then I told you about the memory used for array storage, like numeric arrays versus cell arrays and structs, which have some overhead. And then I talked about the array of structs versus the struct arrays. And from a memory point of view only, a small number of big arrays is better than a really large number of small arrays because each array has its own overhead. So only from a memory point of view, there's other reasons why you might arrange things differently, but that's the way that happens. And I told you about the for loop and which way it's best to loop over the data. And then I showed you these categorical arrays, tables, and strings. And I'm just there's some additional resources. You'll be able to download these slides. And this is just a public service announcement for 2 weeks from now, everything you wanted to know about functions. And so I'd like to encourage you again. I want to thank you first for joining me today. I'd like to encourage you to join me in 2 weeks for a discussion about functions in MATLAB. And then again, 2 sessions in the fall that we'll have, which will be on programming with MATLAB. And from a programming point of view, all the tools you have available. And then the second one then in the fall will be object-oriented programming. And I want to remind you also that if you want to be notified about these, please subscribe to the MATLAB YouTube channel to watch live. Thank you very much.